All right, one, it's October 24th. All right, let's do this. Kth symbol in grammar. We build a table of n rows. We start by writing 0 in the first row. Now in every subsequent row, we look at the previous row and replace each occurrence of 0 with 0, 1, and each occurrence of 1 with 1, 0. For example, n equal to 3. Okay, that's n equal to 3, so I have 3 rows. So first is 0. Second, I say each occurrence of 0 will be replaced by 0, 1. And each occurrence of 0 will be 0, 1. Each 1 will be 1, 0. Given two integers, n and k, return the kth symbol in the nth row of a table of n rows. Okay. So the next one, 0 will be this, 1 will be 1, 0, 0, 1 will be 1, 0, 0 will be 0, 1. Huh. All right. It's a binary tree, right? Yeah, it's a binary tree. 0 will go this, 1 will be 1, 0. 0 will go this, 1 will be 1, 0. 0 is 0, 1, 1 is 1, 0, 1, 0, 0, and 1. Doesn't matter, right? So what we want to find is the nth row. Okay, I mean, I guess, it's just my guess, that a BFS will work. All right, a BFS will work. But it's a complete binary tree, so it is possible to use an array representation. Hence, this is 0, right? 1, 2, 3, 4, 5, 6, right? Or we can, I think start from 1. Yeah, start from 1 would be easier. Right, we start from 1. That would be 2, 3 times 2 times 2 plus 1 times 2 times 2 plus 1. Yeah. So with that, you would just fill it up. But it will be huge. Nah, I don't like that. I don't like it. But I think it's gonna time out, right? Because it's the runtime is basically 2 to the n minus 1, which is huge. So we have to figure out a better way to do this. Basically, n, the kth symbol on the nth. Oh, nth row. It's the last row. It's not any row in between. It's the last row. And everything is 1 indexed. Jeez. And it's the last row. So we want to find the last row. Okay. So the better way will be if we can just find a path down, right? But how do we know the path? If we kth, right? The kth. Hold on, is there any pattern, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? Nth row is the last one, right? We want to find the kth symbol. So let's say the first symbol, right? So this n was 1, 2, 3, 4. So n equal to 4. K equal to 1 is 8, right? And k equal to 2 is 9, right? So if I say I want to find, if I find this, then we can basically track it back, right? We can trace it back. I don't know what this is, right? But we can trace it back. So we can trace it back and then come back down, right? So we just need to find out which one it is. Now at the last one, we know which one is the starting position. We know that, right? N equal to 4, that's 2 to the 4th, right? The starting position is 2 to the 4th. N equal to 3. No, 4 minus 1, right? 4 minus 1. 2 to the n minus 1 is the first value, right? 1 is, n equal to 1 is 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5 is 16. So we have the starting position, and we just plus k minus 1, right? So if k equal to 1, it's going to be this, k equal to 2. So by doing this, we know the last one. And then if it's even, I divide it by 2. If it's odd, I plus 1 divided by 2, right? Or I can just say divided by 2. And we just plus 1. We just plus 1 divided by 2. Or we can do, now I think math.floor does not return an integer. That's the thing. That's a strange thing. Java math floor, I don't think it returns an integer. Yeah, it doesn't return an integer. Yeah, that's not. Yeah, I think I'll just plus 1 divided by 2. Right? Or just plus 1 divided minus 1 divided by 2. Jeez, minus 1 divided by 2. Right? Minus mod 2, right? Divided by 2. And then we can get back to the front. And then we just need to do. Can we know immediately? It'll be hard to do it immediately because we go from top down. So yeah, we do two rounds. Oh, log n. Yeah, that one shall suffice. No, we don't do this. We need to go IntelliJ. Right. So what do? We'll go first. 2, probably math.power. 2 to the n. Or does this return a double? What the hell? Well, anyway, 2 to the n minus 1. Right? Can we, how do we Java cast to int? Oh, that is, I forgot about that. Yes. So we do that, and then plus k minus 1 is the last one. So we can say int path equal to new int that, right? That's the path. And then, oh, that's not right. Yeah, cannot do that. Cannot do that. It has to be a list, unfortunately. Go to new array list. I'd rather just do path.add. Okay, we add that. And then what? While path.get path.size -1 is larger than 1, we do path.add path.get path. Hold a second. Path.get. It doesn't have. Why don't you? Yeah. Why don't you use a stack? You know. Push. Right? We'll push this. And then we say while path.peak. Right? Yeah, that's a stack. Then we'll push path.peak minus path.peak mod 2. Nope. Int it. Divide by 2. You see 11 divided by 2 is 5. Right? Now it is necessary. Wait, hold on. It's integer division, right? Holy crap, is Java integer division? Java divide. Oh yeah, it is integer division. Oh yeah, divide is integer division. Oh, my bad. It actually makes it much easier. Java divide is integer division. So we'll do that. So what this gives me, is the whole path, right? And then what we need to do is find out which one it is and get a result, right? So int res equal to, so we'll start from zero, right? We start from 0, and then we will know the next one. So I think if I start from 0 and this is peak is larger than 1, then equal to 1, come out, right? And then, but I don't want to include 1. I don't want to include 1. And I guess it's fine, right? I guess it's fine. So now we have the next one, and then we say if it's even, right, we go left. If it's odd, we go right. Okay, path dot pop. I don't want the last one, right? So we say while path dot is empty, right? Well, path is not empty. So current, right? Node. So node equal to path dot pop, okay? And if node equal to 1 equal to 0, okay? So that's a left path. Then res shall equal to res equal to 0. If it's equal to 0, then the left is going to be 0. Otherwise, it's 1. Huh. Can I cast it? I guess I can. Can I say like int? Oh, can I cast it to boolean? Shoot. That's fine, right? It will be this. Else, and res equal to 1 equal to 0. Wait, hold on. Then we are same thing. It will be 1 and 0. And then we'll return res at the end. What's the problem here? I don't know. I don't know what the problem is. It's already assigned to this value. Yeah, it's fine. Right? So the last one pop out. We decide this is a even, odd. We go to right. And now return this. I think this should be right. Give it a shot. Yep. But I hope this one can be. Yeah, can we do it better? I mean, this is pretty good already. I'll do this. Right, I put this one in. So we even say one more line. This is extra, right? Can we not do this? I can say larger equal to 3, right? If it's larger equal to 3, we do it. Then we don't have to pop at the end. Oh, that's not right. Larger equal to 3. Right? It's larger equal to 3, and then 1. So 1 doesn't push in. We don't push 1 in. Oh, that's not right. Oh, it still pushed the 1 in. So we always push the 1 in. I want it to be. So it should be larger than 3, right? If it's larger than 3, I do it like a 4. But then it's not right. First one's not right. N equal to 1, k equal to 1. If n equal to 1, k equal to 1 is the first one. And a path. Oh, you already have it inside. All right. Yeah, and I guess it's okay. Just one thing. It's all right. The hell? Is it larger than 1? Larger than 1. Otherwise, you'll put a 0 in. Yeah. Okay, I think I can write something for now. First, find out the exact the table is a complete binary tree, which we can index, right? Which index using 1 for the node, for the root, and thus each left child is double the parent index, while the right child is double plus 1. We find the index of the target value on the last row, then go backwards to produce the path, right? After that, we go from top to bottom following the path to find out what the target value is. O log, it's ON, right? It's ON. Okay, let's give this a shot. Yeah. Not bad. It's not bad at all. This is what I think a perfect medium question. Normal recursion, binary tree traversal. Yeah, you can go back. You know which one you are, so you can go backwards, right? You know if you're a 0 and then you're a left child, so that your parent must be a 0. If you're a 1, your parent must be yeah, that will work. Nah. I'll do another one. Which I don't have. I get the I don't even need, right? Okay, we don't even have to produce a path. We can simply start from the bottom. Oh, you can't. You don't know what the bottom is. Right? You don't know what the bottom is. So you have to start from the top down. Huh. I like my math. I don't want to do recursion this one. I don't even care what this one is. Yeah, it's the same idea, right? And flip it x number of times. Log k. The current k is more than half. Then we flip it. I guess have to go through the previous to figure out. Oh, look at that. I didn't observe that. I observe a binary tree. If we divide any row into two equal halves, then the symbol at each position will be opposite of each other in both halves. We have a 0 in the left half. We'll have 1 at index I. Really? So, 0, 1, 1, 0, 0, 1. Yeah, these are because 0 and 1, right? So this is what generate 1 will generate. So the children generated by 0 and the children generated by 1 is mirror image. Okay, so now going here, so each one will have a mirror image. So when 0 generates and 1 generates, so they're always patterned. They're always, yeah, so at each point, at each position, the 0 and the 1 always match. It's a pair. So every time 0 generates and a 1 generates, it's going to be paired again. So it will always be paired. Okay. Yeah, I can see why it's paired. So our current problem is to find a symbol at a given position k in a given row. If the current position lies in the right half of the current row, then we know this symbol will be the opposite of the symbol present in the left half of the same position. That's correct. And recursively, we will find what is the symbol at this new position in the same row. And if the current symbol lies in the left half, then this symbol will be the same as the symbol in the previous row at the same position. And recursive will find previous row. Wait, hold a second. Oh, because the first half are always the same. So we say if k is larger than this, right, then, well, recursion, n is row, this is the index, so k. So k minus this is the previous, so we'll find that, right? And once we find that, we need to flip it, so that's the flip. So wow, this is interesting. Interesting. Very interesting. From the official solution with the recursion method. The observation is that the first half of each row are always the same from row to row, right? As the second half of each row is always the flipped. It's always the flipped version of the first half. Thus, to find out case grammar nk, we decide whether k is in the first half or second half. If it is in the first half, we simply find the same position in row n-1. Otherwise, we find the flipped version of the same kth location, on the same location in the first half, right? Which means if n is equal to 1, return 0. Otherwise, we say if k we say int row size shall equal to math.power 2 to the n-1, right? And if k is larger than row size divided by 2, I will return case grammar and rows. What's the index? K minus row size divided by 2. Oh, we can call it half divided by 2. Alright, so if it's larger than half, just k minus half. But we need to flip it, which we use this to flip. Otherwise, it will return case grammar n-1. Okay. This is right? Yeah. Yeah, we can probably do this. Or even better, we have, yeah, we can just do 2, right, as half. We can return k is larger than half. Yes, 1 minus case grammar and k minus half. Otherwise, case grammar n-1k. 3 lines. That's also ON. Oh, damn. All right. Now we have the last one. We just need to understand the last one. So the last solution says start with a 0 and flip it x number of times. Flip, flip. Yes. The most challenging aspect is determine the number of flips required. Whenever the current k is more than half of the total number, we flip it and subtract the first half symbols count from k. A flip happens at each subtraction. Thus, the number of flips is equal to the number of subtractions. That is correct. Each row will have some 2 to the a elements. it means half of it will be 2 to the b. Thus, at each step, we subtract 2 to the b from k until k becomes 1. Let me try that one more time. And subtract the first half from, k minus that. Which means at each location, we either do not subtract anything, or we subtract a half, like 2 to the whatever power. We'll subtract that. And the next one, it's inside, so we don't, so that's a 0, right? So this one will be 1, 0, 1, 0, 1, 0, 0, 0. Right? We want is 21. Hold on, we can actually try it. Because only, and this will do. So 21. So we will do, this is 1, right? We flip once, and then we don't flip. Right, so that's the first flip. Then we don't flip, then we flip, and then we don't flip. Is this 21? That's not 21. This is 16. That's 18. What's 21? '21 is, hold on, this is 16, right? Plus 5. This is 20. That's 21. 1 plus 0 times 2 plus times 4 plus, no, 1 times 8. Nah, that's not right. That's 13. '21 is, we want to know how many flips, and each time k is minus the half, right? Well, minus the half, which is 2 times something. No, this should be on the front, right? So it should be a 1, because I flip it. Then we have a 0, because this we don't flip, and this we flip again. Then we don't flip. We don't flip. 4. Right, 2 to the 4 plus 0, 1, 2 to the 2. This is 20. Okay, this is 20. And we're gonna do that until k equal to 1. Right, so we'll say, so the k shall minus something 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 equal to 1, which means k minus 1. So right, so it's k minus 1, so 20. So this determines how many flips you do. So we basically do that, do k minus 1, get into a binary value, count how many ones, right? And if it's even or odd, so this is the, from the third math solution. In the second solution, we observe that each time we flip the value, k must be on the k must be larger, right? Larger than half. And each time we flip k, half of the row size is deducted from k. Thus, the problem can be converted to finding out how many times we need to deduct half the size of some row such that k is reduced to 1. In other words, right? In other words, we need to find out a way to write k minus 1 as a sum of some power of 2's. Now this can be resolved by finding the binary representation of k minus 1. Then the number of 1 bits represent the number of times the value is flipped. So we need to count the number of ones. How do we do that? Do you provide a way to count? Bit count. They do, they have a bit count. I did not know that. Java, bit count. Wow, I can just go directly for bit count. So I can say integer the bit count k minus 1, right? Bit count k minus 1. If it's even, they'll return 0. If it's odd, they'll return 1. O log k. We don't even need to use. Madre mia. It was good, huh? It was very good. I still think my method is not that bad, but yeah, I have to admit these are ridiculously good method. All right, so we're done with this. Good one. You want to write immutability helper. I kind of don't have the gana to write that. I think this is the last one I want to do in JavaScript. Do you want to do it? Yeah, I kind of don't want to do it today. Oh no, I just don't turn off. Oh, I put this one here, flat and nested. Oh, because it has the what's the solution? The recursion, right? Yeah, it has a recursion. I want to try. Yeah, this I never really do it. Do you remember how this one is done? Maybe we don't do it, but I need to go through the thought process. This one is we go through all the set and all the get, right? And we get, oh, I remember a partial object which contains only the values that are, set, right, changed. And then we need to copy it. And we'll go through everything, copy, right? And basically, we say the key, right? The key. Yeah, we'll copy everything, but it's like a shallow copy. And then we will make the change. Yeah. Okay. Yeah, let's hope you can do this tomorrow. Yeah, kind of don't have the gana today. All right, I'll see you guys tomorrow.